Howdy do. Okay, so I had a thought, perhaps even an idea. I need somebody not stupid to tell me why this won't work. For anybody who doesn't know, um, and you might want to turn this off now, you might get bored. Frequencies, right? Think about your cell phone or your Wi-Fi or stuff like that. There's different frequencies. Like for Wi-Fi, it's typically 2.4 gigahertz and 5.8 gigahertz, right? Well, the reason that 2.4 is older and maybe isn't most people think as good is because it is a lower frequency, right? So a lower frequency, and this is what it looks like, the magnetic waves going through the air. You got your peaks and your valleys, your troughs, this is so anyways, you have these sine waves, or more than likely when it's digital, it's more square wave, and it's pulse width modulation, which means that those pulses are actually either a certain amount wide or skinnier, like that. See? Anyways, though, so the advantage of 5.8 over 2.4 gigahertz is you have a much shorter wavelength. Sorry about my horrible handwriting and drawing. So you can fit more data in there, because more times per second, as a matter of fact, 5.8 million, or 100,000, million times per second, this goes back and forth. So if you need to change the width of any of these or whatever, or do, whether it's frequency or amplitude modulation, FM, AM, or whatever, however it's doing it, you can fit more data in there, because they're 5.8 million times per second, that's oscillating. Whereas 2.4 gigahertz, it's like less than half as much. So you can only fit like basically about half as much data. Here's the problem, though, that we keep running into. When you have 5.8 gigahertz, yeah, it's faster, but that's a shorter wavelength. 5.8 gigahertz, I mean, I think you're talking, it's like a couple of inches, the wavelength. I'd need to do the calculation on that. At 2.4 gigahertz, however, you're talking like almost a foot. I think it's like 10 inches. And I can't really remember. But so it's a much longer wavelength. That is better because that gets you much longer distances typically. You have less attenuation. And also it penetrates so much better. Things like walls, leaves of trees, things you wouldn't think it would matter. But when you're talking cell phone signals, Wi-Fi, things like that, longer wavelengths are better. They get through things better, the air, and they travel further. That's why when everybody moved to like 5G cell phone, they have like 1 million of these little cell phone towers everywhere, because it's a much shorter wavelength. This is all microwave. So here's what I thought of. Okay, so anyways, this is an explainer of blah, blah, how everything is and all the issues that everybody, but so I thought about what is another method of data transmission. And of course, there's line of sight, or more commonly, fiber optic, right? You have a fiber optic cable, and it's the same exact thing, though, except instead of the electromagnetic waves traveling through the air, you have photons, you have light traveling through a fiber optic cable, or again, sometimes line of sight, but typically we'll just say fiber. Well, they ran into an issue with that too, even though you have much longer transmission distances with fiber than with copper and stuff like that. They still were seeing some issues about like they were hitting sort of these limits quick. Well, somebody figured out multiplexing, right? Which is smart. Send a different frequency of light on the same fiber. And I'm not going to say it's limitless, but it's because it's certainly, there is both a low and a high end where you can go. But oh my goodness, you can throw so many different frequencies of light. And I guess that's different Kelvin ranges, whatever. And so all these photons going down the same fiber optic cord go, back and forth between the same 2 points, but you can have completely separate streams because they are basically separate frequencies. Well, so how would that apply to what I'm talking about here with just magnetic with RF? Here's what I'm thinking. What if you did multiplex, as crazy as it sounds, and again, somebody smart, tell me why this wouldn't work. What if you, instead of like a typical, let's do a PWM signal like this, what if it was like this? What if you're multiplexing on not just the width of the you're not just modulating the width, but you're also modulating the amplitude at the same time. So then that's double. But what if you could come up with an algorithm, couldn't you, to where so like if it's a 14 what is it? Is it 14-bit? I think PWM signal. You've got, that would be 1, 2, 3, 5 channels. Could you do 5? I would think at least 4 channels of, and again, just it's an algorithm so that on the other end, so you don't have to put every bit of data in there, but you, by modifying it, that you exponentially increase the amount of data you can send in just that same PWM signal on perhaps a lower frequency, right? So all in all, what I'm trying to say is, could you possibly go to a lower frequency, which you have the advantages of much longer transmission ranges, much less hardware required, much less power, just the sheer wattage you have to throw at it, lower cost infrastructure. You're using a lower frequency to transmit your data, but you're modifying the PWM with both the frequency, pulse width, and amplitude modulation to basically sneak in this extra data along those the walls of the width of the if that makes sense, these walls here. Is that something that you could do? How, or am I just completely misthinking that? Or would it be technically like multiplexing, limited, but still multiplexing an RF signal to sneak more data in there and to get the data up to like 5.8 gigahertz, where you still are a lower frequency and you can then have all those advantages? So is that stupid? Somebody tell me. All right, thanks, bye.